Part 3, Polyatomic Ions and Oxoanions. Now we're going to look at polyatomic ions and oxoanions. Polyatomic ions consist of elements that are bonded together and then they carry a charge as a unit. Oxoanions are pretty much the same thing, it's just that these are polyatomic anions that contain lots of oxygen atoms. So let's consider an example of this. Here we have something called silver nitrate, AgNO3. And if you were to put AgNO3 in water, it's very soluble. It would separate into the silver cation and the nitrate anion. So the monatomic cation is silver, and the polyatomic anion is the nitrate anion. The nitrogen and oxygen do not break up in the water. They stay together because they're covalently bonded. So if I look at this ionic combination, I look at the nitrate as consisting of a nitrogen surrounded by the three oxygens, and then that negative sign is distributed around the whole system. You really don't have to think too much about the structure of the nitrate anion, but just remember that NO3 minus stays together as a unit and it contains that negative charge. So here's a table showing you a variety of polyatomic ions. Some of these are cations, some of these are anions, and you could try to memorize these. So you'd have to memorize the anion, its charge, and the name. But what we want to do is use the periodic table to try to use a systematic approach to identifying the various anions and cations. So there are a few, though, we have to memorize. And the first one is cyanide. Cyanide is Cn with a -1 charge. OH minus, this is hydroxide. Here's the acetate anion, CH3COO minus. Sometimes you'll see this with a different configuration or arrangement of the atoms, but wherever you see the 2 carbons, 3 hydrogens, and 2 oxygens with a minus charge, that's typically the acetate anion. Another important one is the oxalate anion, C2O4 minus. So let's consider some examples with these polyatomic anions. So here is some various cyanides. The first one would just be sodium cyanide. Now the next two can have mercury in them, so mercury has different charge states. Notice the cyanide is enclosed in parenthesis in these two. So you have a cyanide with a -1, but I have 2 cyanides, and each one has a -1, so I have a total charge of -2. So I have to have a +2 on my mercury, so that's mercury 2 cyanide. The mercury 1 cyanide, again I have 2 mercuries, they're sharing the +2 charge, so each one has a +1 charge, and I end up with mercury 1 cyanide. Here are some acetates. I've got sodium acetate, and then I have calcium acetate. Notice with the calcium acetate, calcium has a +2 charge on it. Each acetate has a -2 charge on it. The parentheses are enclosing the anion. So if I was to write a formula out where there were no parentheses, that would what that would do is it would eliminate the information. So then I wouldn't be certain that was calcium acetate or not. By enclosing the acetate in parentheses, I know that that's acetate. I know that there are 2 acetates there, and so I can just name the compound calcium acetate. And another way to think about it too is if I were to put this in water, calcium acetate would be very soluble in water. But in water you'd have the calcium cation separate, and then you have the acetate anions separate, and they'd stay together as a CH3COO acetate anion. So let's first look at the oxygen anion. Oxygen has 3 possible charge states. So we've already seen the O-2, and that's our oxide. If we look at another possible state, we have O2-2. This is the peroxide. And what that consists of are 2 oxygens with negative charges bonded together. So here we have a covalent bond between the two oxygens, and then we have two additional electrons, one on each oxygen. That's the peroxide. There's one more state, which is kind of rare, but it's interesting to point out. It's the O2 minus. This is the superoxide. So here I have two oxygens bonded together. They're sharing the negative charge. So we say the charge on each oxygen is minus 1/2. So now we look at some polyatomic cations. The first one is mercury. As an element, mercury can have a +2 charge on it. And so because it can have a variety of charges, we use the Roman numeral 2 to designate the +2 charge state. I also have two mercury atoms bonded together, and they share the +2. So I have a configuration that looks like this, where I have two mercury atoms bonded together. Each one has a +1 charge on it, so I call it mercury 1. Another polyatomic cation starts with ammonia. Now ammonia doesn't have a charge on it, it's a molecule. And here we have NH3, that's ammonia. And if I add a proton to it, it becomes ammonium. So that's one you just sort of have to memorize, but that too is a polyatomic cation. So let's consider an example of this. And here we have mercury chloride. So what's the charge on the mercury? Or better yet, how would I name this compound? So I have mercury 2 with a +2, and I know that because chlorine has a -1, and I have two chlorines. So I need to have two positives to cancel the two negatives. Each mercury is going to share that +2 charge, so you end up with two mercuries in the +1 state, and that means the name of this compound would be mercury 1 chloride. That's often confusing to students because you have the two subscripts, but you end up with a Roman numeral 1, so mercury 1 chloride. All right, so let's explore some patterns with common oxoanions. We're going to consider carbonate, nitrate, silicate, phosphate, sulfate, and chlorate. So there's 6 oxoanions. So when there are two oxoanions involving the same element, the one with the fewer oxygen ends in the ITE. So you kind of have to just memorize this, but NO2 minus is nitrite, SO3 minus 2 is sulfite, and there's some other examples. But then if you add an oxygen to either of these and you don't change the charge, then the ITE ending becomes an ATE ending. So NO2 minus becomes NO3 minus, and we call that nitrate. SO3 minus 2 becomes SO4 minus 2, and we call that sulfate. Let's look at the periodic table and see if we can figure out what's going on in terms of trends. So here I'm going to take boron, carbon, and nitrogen. And if I add 3 oxygen atoms to each of these and choose the stable anion, the boron becomes borate. So BO3 minus 3. Now, remember what happens as I move from left to right on the periodic table. I change the number of electrons or common charge on the anion. So sort of a similar trend happens with the oxoanions. If I go from borate to carbonate, then the number of oxygens remain the same, but the charge changes. So I go from BO3 minus 3 to CO3 minus 2. Here I have nitrate. Well, move over one column, and nitrogen is NO3 minus. Okay, so if you were to think of an O3 or maybe an oxygen O3 anion, well, it wouldn't have any charge. So there's only 3. There's boron, carbon, and nitrogen, and I have borate, carbonate, and nitrate. And as I move from left to right, the charge reduces. If I now remove one oxygen atom from each of these anions, I've got borite, carbonate, and nitrite. Nitrite exists, but borite and carbonate, they don't exist. Those are unstable, and we don't see those at all. Let's move down on the periodic table. So I've got silica, phosphorus, sulfur, and chlorine. So again, I'm going from left to right. And the first oxoanion is silicate. So that's SO4 minus 4. Notice, number one, there's more oxygen atoms. And number two, notice the charge is greater. So silica is going to be larger than the element above it. Carbon is a smaller atom than silica. So silica can handle more oxygen atoms around it. They fit in better. It can also handle a greater charge. So there's a minus 4 charge on this. But the trend is going to follow. So phosphorus is going to be phosphate, and it's going to be a PO4 minus 3. So the charge is reduced, and I have phosphate. You can imagine SO4 minus 2 is going to be sulfate, and ClO3 minus is going to be chlorate. So silicate, phosphate, sulfate, chlorate. Again, you can look at the periodic table, and you can, if you just remember silicate, for example, then you should be able to figure out what happens when we go to phosphorus, sulfur, and chlorine. Okay, so now if I remove an oxygen atom from my silicate, I get silicite. If I remove an oxygen atom from phosphate, I get phosphite. Sulfate becomes sulfite, and chlorate becomes chloride. The halides offer a special series, and if I just start off considering that I can replace my chlorine and chlorate with bromine or iodine, then I can have bromate or I can have iodate. I can do the same thing, remove an oxygen atom, and I can go from chlorite to bromite or iodite. Now here's where things get a little bit different, and I can add an oxygen to, let's say, chlorate, and I get perchlorate. So that would be ClO4 minus. I can also remove an oxygen atom from the halite, and I get hypohalite or hypochlorite, hypobromite, or hypoiodite. So I have 4 possible oxoanions with each halide. You don't see these with fluorine because fluorine is a very relatively small element compared to chlorine, bromine, and iodine. So it doesn't have the same set of oxoanions that chlorine, bromine, and iodine do. Certainly we won't work with any of these in Chem 134. So just as a refresher, if we have a ClO minus, that's hypochlorite. ClO2 minus is chlorite. ClO3 minus is chlorate. And ClO4 minus is perchlorate. So again, with the oxoanions involving the halogens, we need to consider both a prefix and a suffix with these. Sometimes you're going to see a hydrogen with your oxoanion, and you have to be able to name these compounds as well. So for example, consider carbonate, and I'm going to add H plus to it. I get HCO2 minus. So not only did I add the hydrogen, but I also removed one of the negative charges. So I go from carbonate to hydrogen carbonate. Very simple convention. Alternatively, you'll see bicarbonate a lot, and bicarbonate again just means that the hydrogen was added. However, the proper IUPAC name is hydrogen carbonate. So consider an example now where I take that hydrogen carbonate and put it with calcium. I'll need 2 of those. Notice they're in parenthesis. The name I get for this compound now is calcium hydrogen carbonate. Here is another oxoanion. This is phosphate, and the phosphate had 2 hydrogens on it. So in this case, I have to signify that there are 2 hydrogens added. So it's aluminum dihydrogen phosphate. I can drop it down to 1 hydrogen, and in this example now I have sodium hydrogen phosphate. Notice if you consider the charges of the metals, which we would know, and the charge of the anion, which we would know. Looking at only the name, we can determine the formula of the compound.